again, so might not be able to.
February 2017. A British research crew stands on the Brunt ice shelf in Antarctica, 23 kilometers from where they started. They didn't walk. Their entire research station, 8 modules, 2 stories tall, weighing thousands of tons, rolled across the ice on hydraulic skis, towed by bulldozers.
The weather is beautiful today.
They moved because the ground was about to break off and float into the ocean. This is Halley VI. One of 3 stations will follow.
Obviously still very cold, so I'm going to go back inside, but
these aren't just buildings. They're survival machines solving 3 problems. Snow that buries structures in one season, ice that melts beneath warm buildings, and an 80-degree temperature gradient that bleeds fuel. We'll see how engineers turned wind into a tool, waste heat into drinking water, and why fire, not cold, is the deadliest threat. Antarctica is a polar desert. It receives less precipitation than the Sahara, but what little snow falls never melts, and it doesn't fall gently. Katabatic winds, gravity-driven rivers of cold, dense air sliding down from the interior plateau, blast that snow horizontally at speeds exceeding 300 kilometers per hour. The wind doesn't stop. It doesn't pause. Building a standard rectangular building here creates a problem. The flat walls act like a boulder in a river, generating a wind shadow on the downwind side. In that eddy, the wind slows just enough to drop its load. Snow accumulates. A drift forms. Within one winter season, that drift can bury a 2-story building completely. Buried buildings lose their exits. Crews have to tunnel through packed snow just to get outside. Windows vanish, plunging the interior into darkness, even on the brightest summer days. The station requires constant excavation, burning thousands of liters of diesel fuel to run bulldozers that dig out the same drifts repeatedly. The snow keeps coming. The weight increases. The ice, which flows like an extremely slow liquid under pressure, begins to crush the structure from all sides. Early Antarctic bases learned this the hard way. The original South Pole station, built in the 1950s, was buried within a decade. Crews described entering through vertical shafts and crawling through collapsing corridors as the ceiling beams buckled. You cannot fight the wind. You have to use it.
When working on base, your normal day starts at 7.
Halley VI hovers above the ice on hydraulic skis, 8 separate modules connected by flexible corridors. Each module is shaped like a rounded capsule, smooth on all sides, with no flat surfaces for the wind to catch. The entire station looks like a caterpillar made of bright blue and red shipping containers. Every curve was calculated to guide wind over and around the structure without creating eddies. The smooth surfaces offer no purchase for snow, but underneath, the gap between the modules and the ice creates a wind tunnel. As the katabatic wind hits the station, it accelerates through that narrow channel, speeding up to scour velocities. The faster wind picks up any snow that tries to settle and carries it away. The station cleans itself. The wind that would bury a traditional building now acts as a janitor. Halley's crew doesn't dig out snowdrifts. They don't run bulldozers in circles. The station stays clear, year after year, because the same force that creates the problem is redirected to solve it. 1,000 kilometers away, Princess Elizabeth uses the same logic with a different execution. The station sits on exposed rock in the Sor-Rondaine Mountains, one of the rare 2% of Antarctica not covered by ice. But the wind is just as brutal. Before construction, Belgian engineers built a scale model and tested it in a wind tunnel back in Europe. They refined the shape until the airflow was perfect. Smooth acceleration over the curved roof, minimal turbulence at the edges, no standing eddies. The final structure is clad in polished stainless steel, as slippery as glass. Snow doesn't stick. The wind just slides over it. At the South Pole, Amundsen-Scott takes a third approach. The main building is a massive, elongated wing shape, 65,000 square feet, resting on 36 adjustable columns that lift it well above the ice. The building's profile is deliberately angled, like an aircraft wing, so the wind doesn't just pass underneath, it accelerates. The station generates its own wind scour, maintaining a clear zone beneath itself even in the heart of the continent, where the katabatic winds are less extreme, but the snowfall is constant. The winter over crew at Halley describes walking underneath the station during a blizzard. Above them, the wind screams at 200 kilometers per hour. Below, in the scoured channel, the ice is bare and smooth. almost polished. They can see the hydraulic skis, the utility lines, the structural supports, all exposed, all clear. The building floats in the storm. A station interior is maintained at 20 degrees Celsius, comfortable, livable. The ice beneath it sits at negative 30 degrees Celsius or colder, stable and solid for millennia. Put those two surfaces in contact, and you create a heat gradient. Warmth radiates downward. The ice melts. The warm building creates a shallow pool of liquid water directly beneath itself. That water refreezes unevenly as the station shifts and the temperature fluctuates. The ice becomes structurally compromised. Pockets of melt, layers of refrozen slush, uneven surfaces. The building settles into this mess. Floors crack, walls buckle, doors jam shut because the frame has shifted. The air gap isn't just for wind scour, it's thermal isolation. At Halley, the gap between the modules and the ice surface is filled with Antarctic air, negative 40 degrees Celsius or colder. That air is a buffer. Heat radiating from the warm floor above dissipates into the freezing air before it ever reaches the ice. The station never touches the ground. It never melts what it stands on. South Pole's 36 columns work the same way. The supports are made of low-temperature steel alloys, specially formulated to remain strong and flexible at extreme cold. Each column is a sealed tube with minimal surface area touching the ice, just a flat plate at the base, spread wide to distribute the load. There's no continuous path for heat to travel down. Halley's situation is more urgent. The Brunt ice shelf is a floating tongue of glacier extending over the ocean. It moves 400 meters per year, and it doesn't move smoothly. It cracks. In 2016, satellite monitoring detected a chasm forming in the ice, a crack called the Halloween crack because of when it was discovered. It was growing fast. Projections showed it would intersect the station's location within 2 years. When it did, the section of ice shelf Halley sat on would calve, break off, and float away as an iceberg. The winter-over crew at Halley knew the ice was moving. They'd always known. But the Halloween crack changed the timeline from abstract to immediate. Stations before Halley had been lost this way, abandoned to the ice, cut adrift, crushed by pressure ridges, or swallowed when the iceberg eventually flipped. Halley VI was designed for exactly this scenario. Each of the 8 modules sits on a set of wide, flat skis, hydraulic legs that can extend or retract. In normal operation, the legs are extended, lifting the modules off the ice to create the wind scour gap. But when the skis are lowered, the modules rest directly on the ice surface. Then the modules can be towed. In the summer of 2016, the crew began the relocation. The flexible corridors connecting the modules were uncoupled. Each module's skis were lowered flush to the ice. Bulldozers, the same heavy equipment used for cargo transport, were chained to the modules. The convoy moved across the ice shelf to a new site 23 kilometers inland, away from the projected path of the Halloween crack. The modules were repositioned, re-leveled, and reconnected. Utilities were rerouted. The station was operational again by the end of the summer, and in 2019 the Halloween crack continued propagating. The ice where Halley had been sitting broke off. If the station had stayed, it would have been lost. Nomadic architecture. The building isn't anchored. It's temporary by design, always ready to move again when the next crack forms. The crew doesn't fight the ice. They move with it, staying one step ahead of the calving cycle. Princess Elizabeth, bolted to granite bedrock, doesn't have this problem. But building on rock in Antarctica creates its own challenge. You can't pour standard concrete at negative 50 degrees Celsius. It freezes before it can cure, shattering from the inside as water crystals expand. The construction crew had to build heated tents around each foundation site, essentially creating a warm room outdoors. Inside those tents, they mixed concrete with chemical additives that allowed it to set in sub-zero temperatures. Each anchor bolt was drilled deep into the bedrock, creating a permanent bond. The station isn't going anywhere, but it took an entire summer season just to prepare the foundations. Inside a station, 20 degrees Celsius. Outside, negative 60 degrees. The difference is 80 degrees. Heat moves across that gradient constantly, trying to equalize. Every wall, every window, every door resists that flow. Fuel must be shipped to Antarctica by icebreaker during the brief summer window when the sea ice breaks up enough to allow passage. That fuel is stored in giant bladders outside the station, thousands of liters of diesel representing months of operation. Every drop is irreplaceable until the next ship arrives a year later. Wasting heat is wasting fuel. Wasting fuel shortens the operational window. Princess Elizabeth was designed as a passive house, a building so well insulated and airtight that it needs almost no active heating. The walls are 9 layers thick, starting from the outside, a stainless steel shell to resist wind and moisture, a layer of wood for structural strength, then 50 centimeters of high-density foam insulation, more wood, an air barrier membrane, another insulation layer, an interior vapor barrier, and finally, the interior wall surface. Every seam is sealed with specialized gaskets. The entire envelope is continuous, with no gaps, no shortcuts. The goal is to trap the heat generated by people and equipment. 40 people in a station, each radiating about 100 watts of body heat. Computers, kitchen appliances, lights, all generating warmth. In a traditional building, this would be lost. In Princess Elizabeth, it's captured. The building is warm because the waste heat has nowhere to go. But there's a vulnerability, the thermal bridge. Imagine a perfectly insulated wall, 50 centimeters of foam, and then a single steel bolt punched through from inside to outside, connecting a structural beam to the exterior cladding. That bolt becomes a heat highway. Steel conducts heat 1,000 times better than foam. Heat pours through that bolt, radiating out the other side. At the bolt's location, the interior wall surface cools. Moisture in the air condenses on that cold spot. Ice forms. The insulation around the bolt degrades. Engineers are obsessive about preventing thermal bridges. No metal is allowed to span the insulation envelope. Structural steel frames are kept entirely on the interior side of the insulation, where connections to the exterior are necessary. They use fiberglass or composite materials, strong enough to hold the structure together, but poor conductors of heat. Every thermal path is calculated, measured, and eliminated. Windows are the weakest point. A single pane of glass loses heat 10 times faster than an insulated wall. South Pole's windows use quadruple glazing, 4 panes of glass with 3 air gaps between them, but air still conducts some heat, so the gaps are filled with argon or krypton, inert gases that insulate better than air. The window frames are wood or insulated composites, never aluminum, because aluminum would bleed heat straight through. Even with all this, windows are kept small. The station doesn't have panoramic views. It has small, strategic openings for light and morale, and nothing more. At the South Pole, diesel generators sit in a separate building, connected to the main station by an underground utilidor. The generators run in rotation, typically 2 active, 1 or more on standby. They're rated for electrical output, but heat is the primary product. A diesel engine is about 35% efficient at converting fuel into electricity. The other 65% becomes waste heat, hot exhaust, hot engine block, hot coolant. In Antarctica, waste heat is captured in a closed loop of glycol, an anti-freeze solution that can absorb enormous thermal energy without freezing or boiling. That glycol loop is pumped through the station, feeding radiators for space heating, preheating ventilation air from -60 degrees, and melting snow in an insulated tank. Bulldozers dump clean snow onto heated coils. The snow liquefies. Meltwater is filtered, treated, and pumped into the station's water tanks. At the South Pole, they also use a Rodriguez well. They drill a vertical shaft deep into the ice and lower a heated bulb, a large metal sphere with heating elements. The bulb melts the surrounding ice, creating a cavern of liquid water far below the surface, insulated by the ice itself. A pump at the surface draws water up as needed. Princess Elizabeth runs on 100% renewable energy, 9 wind turbines catching katabatic winds, and 400 square meters of solar panels. During the Antarctic summer, the sun never sets. The panels generate surplus stored in a battery bank that powers the station through winter darkness. Solar thermal panels capture heat directly for water heating. But even Princess Elizabeth has backup diesel generators, sealed in a separate room, tested monthly, ready if the renewable system fails. The first rule of Antarctic engineering is redundancy. At the South Pole, multiple generators ensure that if one fails, others pick up the load instantly. The power plant is in a separate fireproof building. If fire breaks out in the main station, the power plant survives. The winter overcrew at Halley needs to go outside. Equipment breaks. Instruments need servicing. but opening a door from the warm interior to the exterior creates problems. Open a single door directly from a 20-degree room to negative 50 degrees, and two things happen. Warm, humid air rushes out, and the moisture flash freezes as hoarfrost on the doorframe, a thick crystalline coating that seals the door shut. Every entrance is a two-door airlock. The crew member steps through the inner door into a mudroom, an unheated buffer zone. The inner door closes. They put on their gear: big red parka, insulated boots, goggles, gloves. This gear stays in the mudroom because bringing frozen gear into a warm room causes condensation that refreezes into ice outside. Once suited, they open the outer door to the Antarctic exterior. The outer door closes. The thermal envelope has never been fully breached. The warm interior air never touched the exterior cold. No frost forms. No heat is lost in bulk. When they return, the process reverses. Outer door, mudroom. Remove and hang the frozen gear. Inner door. The station's heat is its life. You don't bleed it into the air unnecessarily. February. The last plane leaves. The winter overcrew watches it disappear over the horizon. They won't see another plane for 8 months. The sun sets in March and doesn't rise again until September. For 4 months, it's total darkness. For the other 4, it's twilight at best. The cold is manageable. The isolation is harder. The darkness is worse. Humans aren't built for this. Seasonal affective disorder is universal. Circadian rhythms collapse. Sleep schedules drift. Some crew members sleep 12 hours a day. Others can't sleep at all. Depression, irritability, and cabin fever are expected. The station has to be designed for this. Halley VI is bright red and blue. Not for visibility, though that helps. The colors are psychological countermeasures. White is the enemy. Endless white ice, white sky, white horizon. The human brain needs contrast, needs stimulation. The red social module in the center of Halley is a 2-story pod with floor-to-ceiling windows, a bar, a climbing wall, couches, and a lounge. It's deliberately designed to be different from the sleeping modules and the lab modules. It's a third space, a place that isn't work and isn't sleep. Somewhere the crew is pulled to by design. Inside, the station uses full-spectrum lighting, bulbs that mimic the wavelength distribution of sunlight. Standard fluorescent lights make the darkness worse. Full-spectrum lights help regulate melatonin production, keeping circadian rhythms closer to normal. It's not a cure, but it reduces the severity of SAD. South Pole has a small hydroponic greenhouse, a room with racks of LED grow lights and trays of lettuce, tomatoes, and herbs. The crew tends it in shifts. The food itself is secondary. After 3 months of darkness, walking into that room and seeing a living plant is profound. The smell of fresh basil, the color green, the act of watering something alive. The crew talks about it like therapy. Princess Elizabeth has a similar greenhouse and a small library with large windows facing the mountains. The station is designed with distinct zones: work, sleep, and social, each visually and spatially different. Long, monotonous corridors are avoided. You walk through a variety of spaces, each with its own color, lighting, and purpose. These aren't luxuries. They're engineering solutions to a medical problem. The winter overcrew is isolated in a way few humans ever experience. No rescue is possible. If someone has a psychological breakdown, the station needs to absorb it. The design has to reduce the stressors, provide outlets, and give people reasons to leave their rooms and interact. A crew that fractures socially doesn't survive the winter intact. Halley's crew has access to a machine shop, a woodworking shop, and electronics repair stations. If something breaks, they fix it. There's no option to order a replacement part, but the shops also serve another purpose: projects. People build furniture, modify equipment, and design custom tools. It's a productive distraction, something to focus on that isn't the darkness outside. The station is life support, but not just for the body. It's life support for the mind. The walls, the colors, the spaces, they're all part of the system keeping the crew functional until the sun rises and the plane returns. 3 stations, 3 strategies, same survival math. Halley walks away from cracks in the ice. South Pole lifts itself higher as the glacier flows beneath it. Princess Elizabeth sits on bedrock and needs no fuel, but all 3 share the same logic. The wind is your janitor, heat is your currency, and fire is your greatest threat. They all use airlocks, thermal brakes, and closed-loop systems. They all design for the mind as much as the body. The winter overcrews aren't adventurers. They're technicians, cooks, scientists, doctors, people who chose to lock themselves in a metal box for 8 months to keep the research running. They trust the walls, the pipes, the doors. They trust that the engineers who designed these stations understood the stakes. And those engineers did. Every insulated panel, every backup generator, every bright red wall is a piece of survival technology tested against the coldest, windiest, most unforgiving environment on the planet. Antarctica doesn't forgive mistakes. The stations that survive are the ones that stopped fighting the continent and learned to live with it.